Welcome to the Remediation Deep Dive, your source for distilled, impactful knowledge in environmental remediation. We break down the science, the strategies, and the stories shaping our field so you can stay sharp, informed, and one step ahead. I'm Max Flux.
And I'm Sandi.
Today, we are diving deep into really a quite groundbreaking new study. It's from the Remediation Journal. It's titled Tool and Database for Estimating Potential Longevity of Colloidal Activated Carbon Barriers for PFAS in Groundwater. And the authors are Charles J. Newell and his colleagues.
Right. And the core message here, it's pretty significant. Basically, this study presents a simplified way to estimate the longevity of a colloidal activated carbon injection to treat PFAS-contaminated groundwater. Now, it demonstrates a wide variation in longevity can be expected based on site conditions and PFAS species. But, and this is the key part, of 26 actual project sites in the study, the median longevity was on the order of hundreds of years of treatment performance with a single colloidal activated carbon injection.
Hundreds of years. We'll definitely circle back to that. But first, maybe let's set the stage. Why is PFAS, well, such a big deal? Such a challenge?
Yeah, well, PFAS compounds, they're just incredibly mobile in groundwater. They move, and they're very persistent. They just don't break down naturally,
Right.
Then you add in the fact that the regulatory criteria are extremely low, like parts per trillion sometimes.
Tiny amounts.
Exactly. And we currently lack widely proven in situ destructive technologies, so destroying it in place, still very challenging. That combination makes it a really tough remediation problem.
Okay, so faced with that, what are the go-to strategies right now? The proven ones?
Well, traditionally, you're looking at groundwater pump and treat systems, P&T. You pump the water out, treat it above ground.
Okay, standard approach for many contaminants.
Or you can build what are called permeable sorption barriers, PSBs, basically a reactive wall underground.
Got it. And that leads us neatly into these colloidal activated carbon barriers. What exactly are they?
So CAC barriers work by injecting these tiny, tiny activated carbon particles, we're talking 1 to 2 micrometers, into the ground, into the path of the plume.
Really small.
Very small. And they coat the soil grains, they stick to them, forming this adsorptive barrier that grabs the PFAS out of the groundwater as it flows through.
And it seems like this tech is really taking off.
Oh, absolutely. The study mentions over 40 CAC PSBs installed globally already, so it's definitely gaining traction.
40 plus, okay. So let's talk performance. What does the study say about how well they work? What are we measuring?
Well, 2 key things. First is concentration reduction. How much PFAS do they actually remove?
Right.
Across the 26 sites they looked at, the median reduction was around 98% for PFAS overall, and also specifically for PFOA and PFHX excess.
98%. That's huge. Almost complete removal as it passes through.
It's very effective, yeah. But then there's the second metric, and this is where this study really focuses: longevity.
Ah, yes, the hundreds of years part.
Yeah.
How long can these barriers actually keep working? What influences that?
Exactly, and it depends on a few critical things. First, hydrology, basically. How fast the groundwater is moving. That's the Darcy velocity.
Like water speed. Makes sense.
Then chemistry. How well do the specific PFAS compounds stick to the carbon? Are there other contaminants competing for space on the carbon?
Competitive sorption, right?
Also, plume strength. How much PFAS mass is actually hitting the barrier over time? The mass flux.
The incoming load.
Exactly. And then, of course, the regulatory criteria you're trying to meet and how the barrier itself was designed, how thick it is, how much carbon was put in.
So with all those factors, what did they find for longevity? Because those numbers you mentioned earlier were pretty staggering.
They really were. Now, there was a huge range, which you'd expect with different sites. Some calculated longevities were as low as 4 years. Others went over 100,000 years.
Wow. Okay.
But the median values, looking at those 26 real sites, get this: 870 years for PFOS.
870.
Yeah. 150 years for PFOA and 180 years for PFHXS.
Incredible. That really changes the perspective on long-term management.
It does. And interestingly, they note that PFOA often ends up being the limiting factor, especially at AFFF sites, because it doesn't sorb quite as strongly as PFOS.
Okay, good point. So estimating these potentially huge timescales, that sounds like it would normally need complex computer models.
Traditionally, yes. Complex numerical groundwater transport models.
Yeah.
Time-consuming, data-intensive.
Right.
But that's the beauty of this new tool they developed. It's a planning level tool. It gives you a way to get a reasonable estimate much more quickly.
How does it work, basically?
You input the key Site-specific parameters, barrier dimensions, how much CAC you used, the Darcy velocity, the incoming PFAS levels, and it calculates an estimated longevity. It's simplified, but very useful for initial planning.
That sounds incredibly useful.
Yeah.
But we have to acknowledge this is still fairly new technology, right? The oldest sites only have about 7.5 years of data.
That's a really important point to make. Yes, long-term field validation is still ongoing, so there are uncertainties. Well, PFAS concentrations in plumes can change over time. The subsurface is never perfectly uniform, that's hydrogeologic heterogeneity, and the exact sorption behavior can vary.
So how do the authors suggest we handle that uncertainty in practice?
They strongly recommend using safety factors. For example, maybe take the calculated longevity and cut it in half for planning purposes.
Be conservative.
Exactly. And crucially, implement an observational approach. That means robust, long-term monitoring to see how it's actually performing over time and adapt if needed. Combine the prediction with real-world checks.
Okay, so it's not just inject and forget, even if the potential lifespan is centuries.
Definitely not. Vigilance is still key, but the positive outlook here is pretty compelling.
How so?
Well, this tool suggests that maybe over half of the AFFF sites out there could potentially achieve plume control for decades, maybe longer, using the current CAC barrier technology.
Which could be a much more sustainable, less energy-intensive approach than running pump and treat systems for decades upon decades.
Precisely. It offers a potentially very long-term passive solution for many sites.
It really makes you think this ability to even estimate performance over potentially multi-generational timescales using a planning tool is a big shift. It raises the question for me, what kind of future innovations in monitoring, maybe in adaptive management, will we need to really maximize the potential of these long-duration remedies?
A great question for the future.
Well, that's all the time we have for this deep dive. We certainly hope this has given you some valuable insights in the complex and evolving world of PFAS remediation.